Hello. Today we will work on some problems from exercise 16.2, the second part. Last time we did let me write it down. Last time we mainly focused on section 16.2a. We mainly focus on the type of line integral of FDS, right? Which is basically from T1 to T2 of f r t, and then the magnitude of r prime t dt, right? If the curve is managed by rt, and then t from T1 to T2. Okay, we also have implicitly have done some problems with actually f.dr. Now, you may not realize this, but suppose our f is PQR and our dr is dx, dy, dt, dz. Okay, now the dot product here will be integral over curve c of p dx plus q dy plus r dc. We have done that also implicitly. Okay, we have done. We did this part in 16.2, but now I want you to see that's actually just another look of line integral over curve c of vector field f dot dr. Now, in this second part here, you will see we will work on more about that the second integral. We will do this more here with some interpretation. For example, the amount of work is equal to integral over the path being traveled. Okay, and then vector field or force field f dot dr, okay, where this is basically tell us later on the distance traveled, right? The infinitely small distance being traveled. We will also learn in this section, actually toward the very end. I wonder why our textbook didn't emphasize that. Something, in my opinion, very important to emphasize about the curtain area. So suppose I have x-axis here, y-axis here, z-axis here, and then I have a curve in 3 dimension that looks like this, let's say, whose projection maybe looks like, I want to use another color. Let me use this. So this is the path on the ground. Okay, and this is the curtain. So we want to find the area of the curtain. Okay, now then the guy at the bottom here is our RT. Okay, the height is given to us by fxy. Now you will see then the curtain area of the lateral surface is basically the integral over the curve C, okay, of fxy ds. Okay, so that also gives us the integral that we learned last time. That actually also gives us the area of the lateral area of the curve. Okay, now anyway, that's some early review. Let's see. I did some problem already. I noticed that I did some problem in my lecture videos. So in this supplemental video, let's do some problem to add to it. Let's see, for example, number 20. Evaluate the line integral over curve C of f dot dr, okay, where that's the f and this is the r. So rt is t squared t cubed t squared, where the t is between 0 to 1. Okay, so r prime t will be 2t 3t squared 2t. Now how about the vector field f in terms of t? We'll basically replace that xy, xyz into t terms, right? This will be t squared plus t cubed. That's for the first component. Second component is t cubed minus t squared. And the third component will be t squared being squared as t to the fourth. Okay, so now the integral will becomes integral from 0 to 1. We parameterize that by t already, right? Okay, and then we have t squared plus t cubed minus t squared, t to the fourth, dot 2t 3t squared 2t dt. Okay, doing dot product gives us 2t cubed plus 2t to the fourth plus 3t to the fifth minus 3t to the fourth plus 2t to the fifth dt. It's integral from 0 to 1. Let's see. That will be 5t to the fifth minus t to the fourth plus 2t cubed dt. I hope I don't make any algebraic mistake. Okay, but you see that I do the derivative here, and then I plug that RT into the F, right? It makes the vector field becomes a vector function of T. Right now, I substitute the F and the R, the dr. Okay, and then I apply the dot product. This is what I get, and this will give us 5 over 6 minus 1/5 plus 2/4. I think the LCD is 60, huh? So 1 over 60, 50 here, minus 12 plus 30. What will that be? 80 minus 12 is 68. So that's 68 over 60 reduced by 4. So this is what I get. Okay, again, assuming that I don't make any, yeah, recently I make a lot of algebraic mistake, but the underlying idea is basically the same, like that. Okay, that's for number 20. Let's go on with number 30. Number 30, evaluate. That's part A, evaluate. There's part B here, but as I remember, the part B requires us to use some kind of like software. So I just do part A. Evaluate the line integral over curve C f dot dr, where the f is that and then rt is this. So r prime t will be 2, 3, negative 2t. And the vector field f as a function of t is now 2t, negative c means what? T squared. Y will be 3t. Okay, this is our x, this is our y, this is our z. Okay, for ijk, right? Now, next, then what happened with the integral? So the integral over curve C of f dot dr will be integral from negative 1 to 1. The vector field is 2t t squared 3t dot 2, 3, negative 2t dt. And then I will do the dot product. That will be 4t plus 3t squared minus 6t squared dt. That is integral -1 to 1 of 4t minus 3t squared dt. Well, this is an odd function over opposite domains, so that will become 0, right? Okay, and we will get double of this. That will be 2 times -3 over 3t cubed from 0 to 1. Well, that's because I do this. That's 2 times integral from 0 to 1 of -3t squared dt. Okay, so we get this is equals to -2. Okay. Let's go on. Number 32. Now we have some work to do. Number 32a, find the work done by the force field on particle that move once around the circle. This is the circle. This is a circle with radius 2, counterclockwise. So let's parameterize that. So curve C is given by RT. Oh, by the way, that's one skill that you need to start developing. Okay, they will tell you, okay, this particle will move around the circle counterclockwise. You need to be able to come up with the parameterization of that path. Okay, that's a circle with radius 2 going counterclockwise, right? Okay, so we will use 2 cosine t, 2 sine t. The t is, it's one circle, right? Once around the circle. So the t will be from 0 to 2 pi. Okay, so r prime t will be -2 sine t and comma 2 cosine t. The vector field now as a function of t becomes x squared 4 cosine squared t, comma, the y component is xy, so that will be 4 cosine t sine t. So the integral over closed curve f of f dot dr, that will be integral from 0 to 2 pi 4 cosine squared t, comma 4 cosine t sine t dot -2 sine t 2 cosine t dt. That will be integral from 0 to 2 pi of -8 cosine squared t sine t plus 8, oh, cosine squared t sine t dt, but that's 0 though. Okay, so this will be 0 then, so no work. No work. I'm surprised with this result too, to be honest with you. Yeah, so no work. So maybe when it goes once this way, it actually spends some energy, some work, and then when it goes backward, you actually gain, save some energy that happens to be canceling out. Maybe that's the case, maybe. But is it possible for us for the particle to have a total of 0 work? It's possible. Okay, that's possible. Next, number 36. Find the mass and center of mass of wire in the shape of helix. This is the, okay, that will be the path, That's the parameterization. The curve is given by RT, T, cosine t sine t. The t is from 0 to 2 pi. The density, so the rho at any point is equal to, so not proportional, but exactly equal to the square of the distance from origin. The distance from origin is square root of x squared plus y squared plus c squared. You square this. So this is x squared plus y squared plus c squared. Now, if we parameterize that by t, that will be t squared plus cosine squared t plus sine squared t. That is equal to t squared plus 1. I'm sorry. So the mass of this curve C of this wire will be integral, supposed to be integral over the curve of the density I'm sorry density ds. Okay, so in between I need to find the r prime t. So for the ds, right, so this will be integral from 0 to 2 pi. The phi in terms of t is t squared plus 1. I need to find r prime t and find the magnitude to find the ds later on. That's 1 negative sine t cosine t. The magnitude will be equal to 2. I hope you can see why it's 2. So this is 2 dt. Okay, so this will be 2 times 1/3 t cubed plus t from 0 to 2 pi. 2 times, I'm sorry, square root of 2, not 2. So that's 8 pi cubed over 3 plus 2 pi. Okay, that's the mass. How about center of mass? The center of mass is it's 3-dimensional. A lot of work. I'm sorry, my allergy comes. It's kind of bothering me right now. So moment with respect to xy plane will be the same integral, but we insert the c. Okay, moment with respect to xy plane is the distance from xy plane, which is z. Okay, then I will substitute that in. That's integral from 0 to 2 pi. What is our c? Our c is sine t integral t squared plus 1 the square root of 2. Oh no, that's with parentheses, not with square root. Square root of 2 dt. Okay, I can break this down into, should I do that breakdown or I don't need to? I think I don't need to. I definitely need integration by parts though. So square root of 2, let me take that out. Then polynomial first, and then trigonometry dt. I want to do tabular method. So this will be square root of 2 bracket negative t squared plus 1 cosine t plus 2t sine t plus 2 cosine t from 0 to 2 pi. And then when I plug that in at 2 pi, that will be negative 4 pi squared plus 1, and then plus 0 plus 2, that's for the first part, minus, when it is 0, that will be negative 1, 0, plus 2. So we get the canceling this, canceling that, I get negative 4 pi squared square root of 2. That's impossible though, because the domain is positive, right? From 0 to 2 pi. Do I make any miscomputation somewhere? Integral. I don't see any problem. Which is strange. The moment should not be negative here. I need to see what's wrong. Okay, give me a second. From 0 to 2 pi, that's correct. Oh, the c may be negative. The z may be negative. My bad. So yeah, that's okay. So the c may be negative. My bad. In fact, the c bar will be negative 4 pi squared square root of 2 over the mass, which is square root of 2 8 pi cube over 3 plus 2 pi. I think at least I can cancel the square root of 2. Let me multiply by 3. That will give me, if I multiply by 3, that will be negative 12 pi squared over 8 pi cube plus 6 pi. Oh, we have common factor 2 and pi, huh? So there will be 6 pi, 4 pi squared plus 3. That's the C bar. So we get the moment with respect to xy plane first. Imagine this. So the moment with respect to xy plane, let's say that's the coordinate here. Okay, so the distance from xy plane will be denoted by, will be equal to z, right? Okay. So we insert c into that moment. Now then, the c bar, the z component of the center of mass, is given by that. You know what? Let me grab some drink. Give me a second. Let me see. Hold on. I'm sorry. Let me go on. Then how about if I want to find x bar, then that will be the moment with respect to yc plane over the mass, right? But the moment with respect to yc plane is that integral over curve C of x rho ds. What is our x? It's from 0 to 2 pi. Our x is what? T, as I remember. Yeah, our x is t. Our rho is t squared plus 1. Our ds is square root of 2 dt, right? Okay, so this will be square root of 2 integral from 0 to 2 pi of t cubed plus t dt. That's square root of 2 times 1/4 t to the 4th plus 1/2 t squared from 0 to 2 pi. What will this be? That's 4 pi to the 4th. Is it right? 16 divided by 4. Yeah, 4 pi to the 4th plus 2 pi squared. I can factor the 2 pi, huh? 2 pi squared. 2 square root of 2 pi squared. That will be 2 pi squared plus 1. So the x bar will be 2 square root of 2 pi squared, 2 pi squared plus 1 over, what is the mass again? Square root of 2, 8 pi cube over 3 plus 2 pi. I should just simplify that earlier. Square root of 2 cancels. Let me factor the 2 out, multiplied by 3 on the top and the bottom. Will give me 6 pi squared, 2 pi squared plus 1 over 8 pi cube plus 6 pi. I can factor and cancel 2 pi. If I cancel 2 pi, there will be 4 pi squared plus 3. I think that's the furthest we can go. That's for the x bar. And then you compute the y bar yourself, okay? You compute your y bar yourself. So the center of mass, x bar, y bar, c bar, equals to 3 pi, 2 pi squared plus 1 over 4 pi squared plus 3 for the x component. The y bar, you look for it yourself. And then the c bar is 6 pi of negative 6 pi over 4 pi squared plus 3. I really question my c bar though. I was expecting that to be 0, but I don't know. I look at the computation, seems like nothing wrong. Okay, so the y bar, you look for it yourself. Let's go on with number 40. Number 40. Let me give myself some space so that I don't feel like it's crowded. Number 40, find the work done by the force field F. Let me write it down. The force field, the vector field right now, xy is given by x squared ye to the x on a particle that moves along a parabola c given by x equals to y squared plus 1 from 1, 0 to 1. Let's parameterize this. We can use y as the parameterization, right? So RT is given by, if the y is t, then the x will be t squared plus 1, right? And then with the y from 0, it means the y, which is t, is from 0 to t equals to 1. Okay, now then r prime t will be 2t comma 1, and the work is equals to integral over curve c of f dot dr, which is integral from 0 to 1. The f will be x squared, and then ye to the x dot, the dr is 2t1 dt. Oh, you know what? Let me move it below. then multiply that in. This is integral from 0 to 1 of 2t times t squared plus 1 squared plus t e to the t squared plus 1 dt. Let's do some substitution. So u equals to t squared plus 1 du will be 2t dt. So this will be integral. Oh, the u0 is 1, u1 is 2. So this is from 1 to 2. Okay, u squared du, that's for the first part. Okay, and actually I can just put them together. U squared, yeah, let me write it down. U squared du plus e to the u du over 2. Now I factor the du integral from, it's integral from 1 to 2 of u squared plus 1/2 e to the u du. That's 1/3 u cubed plus 1/2 u e, 1/2 e to the u from 1 to 2. Okay, anything after that is just computation, right? Okay, so when u equals to 2, what happened? When u equals to 2, I get 8 over 3 plus e squared over 2 minus, when u equals to 1 is 1/3 plus e over 2. So that will be 7/3 plus e squared over 2 minus e over 2. Okay, that's the amount of work. That's for number 40. Is it okay though? I hope you understand what I did. Well, you can just separate this into two integrations if you want to, you know, but I think because they happen to use the same substitution, we can just use the same u in the same integrals. Let's go on with number 42. The force exerted by an electric charge at the origin on charged particle at a point xyz with position vector r is, so the vector field of rt, which they just use r, is equal to a constant multiple of r over the magnitude of rt being q. Okay, find the work done as a particle moving along straight line. So the path is a line segment from 200 to 215. So this is plus t times 0, 1, 5, where the t is from 0 to 1. Right? Okay, so r prime t will be just the 0, 1, 5. The direction vector is a straight line. Okay, so the work will be integral over curve C of force field dot dr. And when because we parameterize with t, that will be from 0 to 1. The force field F will be k times RT. What is RT again? RT is 2t 5t, Is it right? You put this together, 2t and 5t over the magnitude of that. I'm supposed to do that separately. So magnitude of RT will be square root of 2 squared plus t squared plus 25t squared. That's square root of 4 plus 26t squared. So this is 4 plus 26t squared being cubed times, actually supposed to be dot, r prime t, that's 0, 1, 5 dt. K times, what is that? It's 26t on the top over 4 plus 26t squared to the power of 3 half dt. Oh, I think this is an easy substitution, right? So u equals to 4 plus 26t squared du will then be 2 times 26t dt. u0 is 4 and u1 is 30. Now the integral becomes, remember when you do substitution on the definite integral, you need to change the limit of integration at the same time. Okay, so this is u to the power of 3 half, and then I will grab this guy together, call this du over 2. Okay, so this is k over 2 integral from 4 to 30 of u to the power of negative 3 half du. That's k over 2 times negative 2, u to the power of negative 1 half from 4 to 30. Okay, so that will be negative k, and then negative k, and then 1 over square root of 30 minus 1 over square root of 4. That's what I get. Or we can say this is k times 1 half minus 1 over square root of 30. Ooh, that's ugly. Yeah, simplify from there. Should I do that? I'm so lazy though. This is k, make it 30. So this will be 15 minus square root of 30 over 30. Like that. Okay, that's the work. Again, I show you the technique. I may have made some miscomputation. I don't think so in this case though. The one I really wonder is this one, okay, the C bar. But I don't see any mistake here. Did I make mistake in my integration by parts 2t? Yeah, that's correct. Sin t, I pulled the square root of 2 out. Yeah. Really, I don't see any mistake there. I deal with that later. Okay, let's see number 44. An object with mass m with position function rt moves in that position function. Now find the work. The work equals to integral over the curve of force field dot dr. Now we have that rt is given by a sine t, b cosine t, and ct. The t is from 0 to pi over 2. So the r prime t, I think that one is on the easier side. It says a cosine t, negative b sine t, and c, right? That one is okay. But how about the force field? The force field, hold on. The force equals to the mass times acceleration, huh? Okay, so the acceleration here is at, which is r double prime. Okay, so that will be negative a sine t negative b cosine t 0. Okay, and then the mass is m. So the force field is m times that factor. Let me factor the negative out. A sine t, b cosine t 0. Now let's come back here. You know what? I'm supposed to do this first. Move it here. Okay, and then maybe this one. Move it here. I think that's better that way, right? Okay, so the work equals to integral over curve C of f dot dr, but the C is parameterized from 0 to pi over 2. The force field is negative m a sine t b cosine t 0 dot r prime, r prime. So because the dr, right? So that will be a cosine t negative b sine t dt. That is negative m integral from 0 to pi over 2 of a squared cosine t sine t minus b squared cosine t sine t dt. Oh, we have common factor a squared minus b squared there. So this is m times b squared minus a squared integral 0 to pi over 2 of cosine t sine t dt, which is half of double angle. So this is m over 2, the mass over 2b squared minus a squared integral from 0 to pi over 2 sine 2t dt. But integral of that will be another 1/2, huh? That's 1/2 negative cosine 2t from 0 to pi over 2. That will be negative cosine pi is 1 plus cosine 0. That's another one. So that's 2. Okay, so that will be the mass over 2b squared minus a squared. You know what? I factored the negative already, so this should be positive here. I'm sorry. So it should be positive here. Should be positive here, positive here, positive here, positive here, positive here. Okay. Yeah. So that's the amount of work. That's the amount of work. Hold on. The negative here for this is that's the one I pull out, but there's oh sure, that's correct. So originally it was correct. Let me just back. Am I right with the back? Now am I good? Yeah. So this is, I almost make what I already get right, make it wrong. Okay, that's the amount of work. Okay. Number 45. Then this question is actually fun. Let's start with number 45 first. Number 45. I look at this question. I could answer number 45 by physics right away. Okay, let's if you think about physics, how we do it by physics, right? We have somebody with the person is 160 pounds plus the paint, the can of paint is 25 pounds. Put together you have 185 pounds, right? And then you go up the helical staircase. So imagine if you have a staircase helical like that. Okay, and the height is 90 feet. Okay, how much work is done? Well, the work should be done against the gravity, if you think about it, right? The work is done against the gravity. So the work basically equals to 185 pounds times 90 feet, right? That's the work. Okay, what is that, by the way? If I use my calculator, 185 times 90. Give me a second. 185 times 90. That will be 16,650 pound feet. Okay, pound times feet to be more precise. That's the amount of work if we do it by physics. It turns out math wants to see that further, or by calculus 3. We want to parameterize that. Okay, we want to parameterize that. Notice that the force in force field is actually 0 in x direction, 0 in the y direction, and then 185 in the c direction. Okay, in pound. Okay, and then the path RT, 90 feet divided by 3 complete revolutions, right? So complete revolutions, so the T will be up to 6 pi, 3 times 2 pi, right? Okay, and the silo with radius 20 feet, so that will be 20 cosine T in the X component, 20 sine T in the Y component, and then the Z component will be 90 feet divided by what is that? 90 feet divided by that's 30 feet each. So 30, like this. Let's see. So I need to travel this in 6 pi. So 90 feet divided by 6 pi times t. Okay. Divided by 6 pi times t. Which we can simplify to be, let me simplify because it could be very nasty later on. So sine t, and then reduced by 6, it will be 15t over pi. Okay. Now then from here we do, what is r prime t? R prime t is negative 20 sine t, 20 cosine t, and 15 over pi. So the work will be integral from 0 to 6 pi, the force field 0, 0, 185, dot negative 20 sine t, 20 cosine t, 15 over pi dt. 0 to 6 pi, that will be 0 plus 0 plus 185 times 15 over pi. 15 over pi dt, but this will be equals to 185 times 15 over pi times 6 pi, right? The pi cancel, this becomes 90, so 185 times 90, that's 16,650 foot-pound or pound-foot. Okay, number 45, I think is in the easier side. Is in the easier side. Number 46 is the challenging one. I don't think it's easier done by physics. I don't think it's easier done by physics. You will see that's actually very doable by physics. I'm not questioning the physics one, but math tends to be more picky. If you have a three-dimensional movement, it should be expressed in 3 dimensions. Okay, so what happens if you have a hole in the can, okay, and you have 9 pounds of paint leaks steadily out. In other words, a total of 9 pounds leaking with a linear speed. In other words, so what happened is, suppose we parameterize that the force. Suppose we parameterize that using T, then the total weight minus 9 pounds loss. So you subtract by 9 pounds over 6 pi times T. That's the force. Okay, that's the force. Okay. Basically, at time T, it will lose already 9 pounds, right? Okay. Now, but the parameterization is the same. So the work will be integral from 0 to 6 pi 0, 0, 185 minus 3 over 2 pi times t dot negative 20 sine t. Actually, we don't worry about the first 2 terms because when you dot that with 0, it will be just 0. This is 15 over pi dt, right? The same path, okay? Now, this will give us integral from 0 to 6 pi of 185 minus 3t over 2 pi times 15 over pi dt. Now, I want to show you that this guy here will give us the earlier number. Okay, will give us the earlier number, which is 16,650 minus the integral of 0 to 6 pi of negative 45t over 2 pi squared dt. Okay, no more negative. I'm sorry, no more negative. The negative already factor out. Then this will be 16,650 minus, so that will be 45 over 4 pi squared t squared from 0 to 6 pi. Right? Which will be 16,650 minus 45 over 4 pi squared times 36 pi squared. That's 9, huh? That's 9. So 16,650 minus 45 times 9. What is 45 times 9? 4 or 5? So we get 16,245 pound feet. Okay, this is for number 46. I'm a bit tired. Let me go on with number 48. Oh, this is the last one. Okay, I have more. Okay, number 48. The base of circular fence with radius 10 is given by this parameterization here. Okay, so it is actually a circular fence with radius 10. Okay, so we can path that with RT equals to 10 cosine t, 10 sine t, where the t is, of course, from 0 to 2 pi because it's one cycle. The height is given by that. The height of that fence is given by 4 plus 0.01 times x squared minus y squared. If I parameterize that using by t, it will be 4 plus 0.01 times 100 cosine squared t minus 100 sine squared t. I can factor the 100. Actually, that will kill the 0.01. That gives us 4 plus cosine squared t minus sine squared t. But that is actually cosine 2t. Huh? Okay. That's the height at any given time t, or any given, any parameterized t. So the height varies from 3 to 5, which is true. When t is 45 degree, for example, that will be 4. Yeah, this varies from between -1 to 1, right? Okay, so the height will be from 3 to 5. Okay. Suppose 1 liter of paint covers 100 square meter. Sketch the fence. Determine how much paint you need if you paint both sides of the fence. Hold on. So in 3-dimension, let me try to grab 3-dimensional view. Okay. So let's say this is our x, y, and z. We have a circle on the base, approximately like this. With the height, when t equals to 0, that will be 5. When t equals to pi over 2, that's 3. So it seems like it's like this. It's getting lower. From here it goes getting lower, and then later on it comes up again. Okay, sketch the fence. So the fence is approximately something looks like this. Make the top thicker so that we know that it goes up to what. Okay, on the behind side, so the fence approximately looks like that. Okay, now how much paint is needed? We need to find the area first, huh? So to find the area of the fence is equal to integral over the path of the height ds. That means I need to find the r prime t and then the magnitude. R prime t is -10 sine t, 10 cosine t. The magnitude, I can factor the 10, and I found out, yeah, that's 10, right? Okay, that's the r prime t. The height, we already parameterized that. Okay, then I can plug that in, integral from 0 to 2 pi 4 plus cosine 2t, and then r prime t is 10 dt. I know this will be 0, right? So the area will be 40 times 2 pi. 40 times 2 pi, that's 80 pi meter squared. Okay, so what is the amount of paint? The amount of paint amount of paint will be the total area divided by 100 square meter. Okay, so what will that be? 4 pi over 5 liter. Okay, that's the, so what is that? 4 5 times pi, 4/5 times pi. Okay, so that's the amount of paint. If oh, hold on. If you paint both sides, oh, okay. Hold on. Both sides means I need to multiply this by 2. So this will be 8 pi over 5 liters, 1.6 pi liter. Okay, that's the amount of paint. If you only one side, then yeah, 4 pi over 5 only. Okay, that's for this 16.2. I think I do more than what is explained in my lecture videos. Okay, because you see the application of this line integral over force field to find the work. Okay, and you also see the application of the line integral over function, in this case the height function, that give us the lateral area. Amount of paint is basically just variation of this question, you know. Okay, that's for this 16.2, the second part.